All right, so let's now explore even more fun stuff with the rules for finding derivatives. So now after looking at the power rule and those other basic rules as in the previous lecture that we have looked at, then now I am going to introduce the product rule. Right, the product rule and the quotient rule. So these rules are all about the techniques, the methods to find derivative quickly, effectively, and efficiently, and completely bypass the limits definition. Okay, so again, let me promote a starting problem. So now let's say we're looking at a given function and we're asked to find the derivative. So let's say we're looking at x squared and in product with, in parentheses, 2x to the fourth minus 3x squared. Okay, and here's our function, and we want to find dy dx. We want to find the derivative for this function here. So at first, looking at something like this, well, and anyone after learning my video on the power rule and those other basic rules, looking at this, you're gonna feel that's easy. Well, nothing challenging about this, nothing special about this problem. Why don't we, so before taking derivative, we can play a trick that we can just simply multiply and distribute, because what we notice here is that x squared is being in product with this expression, this lengthy expression inside of the parentheses. So x squared multiplied with quantity 2x to the fourth minus 3x squared. And so right at first sight, anyone can already have in mind a plan as following. Why don't we just distribute that x squared? So distribute that x squared to each side here, distributing that x squared to each term here. Then we're looking at 2x to the 6 minus, and now the 3x to the fourth, easily. And then now, after distributing that x squared into each term, then we can go ahead and take the derivative of that. So dy dx is simply the derivative 2x to the 6 minus 3x to the fourth. And derivative rule that we've learned, the difference rule is right here, allowed us to find the derivative here term by term. So first term the first term would become 12x to the fifth and minus 12x to the third power. And there we go, we have the answer. That's the end of our little problem. I see no motivation for getting into a new method, for learning a new method. We already found our methods right here, even though we have a product. Okay, so things seems easy that everybody start believing that we can just stay with foiling out and distributing and things remains easy. But that doesn't stay for too long. Things remains easy until now we hit a problem like this. So let's say I am going to bring up another problem. How about y equals, and here what I'm looking at is x cubed minus 4x plus 1 in quantity, multiply with, and 4x to the fifth minus 3x squared plus 5. Okay. And now we have another product, a different product. Okay, but with this product here, now we can still foil out. But now foiling out is going to give us some disadvantage in terms of time and in terms of efficiency, because it takes a lot of time and it takes way too much effort. and it's lengthy and it's easy to make mistakes as we are going along with this lengthy foiling work right here. And so in that case, at this point now, we start having that, we start feeling that we need a new method to directly handle the derivative right out from this product without multiplying terms out. So now allow me to introduce the derivative rule that we refer to as the product rule, which means it's a rule to find derivative directly out of a product like this. What I see here is we have a product of two separate functions. Each function here has three terms. It could be more than that. It could be even more complicated than that. But now how about in this product? Let me name this function here some function u of x. Okay? And the other function involved in our product here, let me name that other function here v of x. Okay? And so the idea of taking the derivative. So for now, naming these two functions is just for me to, at the end, put up a formal formulation of the product rule. But for now, the way how we take derivative as the new method here, what I'm going to be doing, I'll be first take the derivative. I'll be taking the derivative of my first function in this current product here. So the derivative of meanings, I am going now to take the derivative of x cubed minus 4x plus 1. Take that derivative first. But then I am going to multiply with the other function, 4x to the fifth minus 3x squared plus 5. The other function, the remaining part, the remaining factor of my product, I'm going to keep it the same. I only take the derivative of the first one, of the first function that stayed in our product here. But then, this is actually only halfway of our product rule. So the product rule says we're going to now need to add. So these are a couple of special elements right here. Okay, so now I'm going to need to add. All right, and so continuing with my current work there, I am going to now keep my first function here, the x cubed minus 4x plus 1. Okay, I'm going to keep that first factor the same way it was originally, but now I'm going to multiply in product with 4x to the fifth minus x squared plus 5. But now I am going to proceed on the derivative of that. So have a close look at this. So what it says here is that I need to, this is now equivalent to, I need to take u prime, the derivative of the u function, and then multiply with v of x, keeping v the same, and then add, and this work right here is u of x, no prime, multiply with v prime of x. And that's the setup for that. And so I just directly introduced the way how we handle that problem. And so in that way, allow me now to move over to the other board. So continuing into the other board that we have, then dy dx in that case. So it is going to give me 3x squared minus 4. Okay. Multiply with 4x to the fifth minus 3x squared plus 5. So this is again our result, our outcome of the u prime from the previous step. And then this is v of x. Then I need to add with, from the previous step, there's an addition problem right there. And now the next part, and since I'm running short of board space, I have to cut into the next line right here. But I am going to keep my first function the same, x cubed minus 4x plus 1. But now I am going to multiply. So carrying over from the previous step, now we're looking at 20 x to the fourth power minus 6x and plus 0. Okay, and so this part right here is the u of x being carried from the previous step, and right here it is our v prime of x, and these two are in product. Okay, and so at this point, after seeing a few steps right here, this is legally our final derivative of the product above. Okay, it is legally the derivative of our product above. So now let's formulate what's happening in our formula here. Right from the beginning of our work, then we were in the need of the reason I wrote u and v, because now generally speaking, the problem we were doing describes a product of two functions, and what we were doing there was to take the derivative of the entire overall function as the product of u and v. And so the work that we broke down right there, so now according to that, what's now legally to be the product rule, the rule to take derivative directly from a product of two functions, then we are going to first take the derivative of u. That's why I'm producing that u prime right here. Then that derivative of u must be multiplied with v. So u prime times v. But then product rule says further we need to add with u of x, which is the original u function, multiplied with v prime. And so this is the famous product rule. Okay, so what I just wrote there is the famous product rule. And products rule. Okay. And so now, in the way how we discover this rule here, let's look back at the example we brought up earlier. Okay, so back to that very beginning problem that I brought up, x squared in product with 2x to the fourth minus 3x squared right there. Okay, so clearly speaking, this is a product of two separate functions. We can regard to this as u of x, and we can regard to this right here as this is u and this is v, and according to the way how our function is being defined, what we have here is a product of u and v. So our problem in the beginning I brought up was that it was the problem where we want to find the derivative of this function. So now we already found the derivative of this function. It was so we found dy dx to be 12 x to the fifth, okay, and minus 12 x cubed. So that's what we found earlier, okay. And what we did there, as a quick reminder, we multiplied before we took the derivative. We multiplied the x squared into each term of our lengthy sum right here. All right. And so, but now let's redo the problem. I don't always do this, but there's a reason why I want to show everybody. And so in the end, this is a product. So let's apply that famous product rule we just now learned. So seeing this entire problem as a product of u, where u is here, and multiply with v, and v is here, the entire two terms thingy. So I am going to find dy dx according to the product rule. And so the product rule says, here's my u, so I need to find the derivative of u first. So now it's just an indicator. I am going to take the derivative of x squared, and I am going to multiply with the function v, which is 2x to the fourth minus 3x squared, keeping it the same. But then that is only half of our product rule, and so now I am going to add. So the next step, I am going to keep x squared the same, because that's now u of x. And I am going to multiply with the derivative of 2x to the fourth minus 3x squared. Okay, and now we are ready for the next step. All right, so on my other board there, carrying over from the next step, then dy dx now is going to look as following. So 2x as the derivative of x squared. Now multiply with 2x to the fourth minus 3x squared. Okay, plus, and then for the other function, for the other part, we're going to keep x squared the same. And now the derivative of x, of 2x to the fourth minus 3x squared from the previous step is now going to be 8x cubed minus 6x. Okay? And so, once again, let me bring up the other board for everybody to quickly double check with your steps and my steps. Like that. Okay? So this is the setup that directly applies the product rule. Okay, so I put a prime on the x squared simply because x squared here is playing the role of our v, I mean our u function in the product rule, and then all that here, that 2x to the fourth minus 3x squared is in the role of our v of x function. Okay, and then the same for this. Now x squared is in the role of the u, but now I put the prime on my function v like that, and so for that, for the other work, that's how it turns out. And so as far as getting the derivative, we're done. We're done. But now immediately, it's the way it is, and we are math people. We're learning math to eventually, become at some moderate level of doing math. And considering any of you learning math here, then any of you is a mathematician on your own. So why does this answer look so different with the earlier answer we have found? Why does this answer here look a lot longer? Okay, so no worries. This is how it looks. It takes a little algebra again. But so the 2x here, so now I'm talking about we already had the final answer as our derivative using the product rule. But how can we show that this answer is exactly the same as the earlier answer, the other answer that we found earlier? So now I can just go ahead and distribute this 2x into these two terms. So really dy dx can be rewritten as 4x to the fifth power minus 6x cubed. That takes care of distributing the 2x for each of these two terms. Then we're going to add, and maybe let's keep parentheses here. And now x squared is going to be distributed for each of these two terms right here. So now I'm looking at 8x to the fifth minus, now x squared times 6x is going to be 6x cubed. And now it's adding between these two groups of parentheses. So now we're looking at 4x to the fifth. Feel free to remove the parentheses without worrying about sign change. And now plus 8x to the fifth minus 6x cubed. And now the next responsibility is to combine like terms. So we're looking at 4x to the fifth plus 8x to the fifth. All together, that's 12x to the fifth. And then minus 6x cubed minus 6x cubed all together is a minus 12x cubed. So in the end, we landing into the exact same answer as how we've done that using the earlier method. Okay, so I am not saying that well, for now, probably watching this video, many viewers are not very convinced, many learners are not very convinced about doing the product rule is going to be a lot more effective than doing the distributing things out, because in this problem we had this shorter answer before we used the longer the product rule. But there are times when we run into the kind of products where and just a moment ago we did the kind of problem where it was a product where nobody would be patient to factor through like that or to multiply through. And so in that way the product rule would be the more direct answer in that case. Okay, and so let's now look into an example of how we can apply our product rule, how we can work with our product rule. So now we are at our example 1. Okay, and so let's find f of x or dy dx. Okay, problem A right here. So for our function, this time let's strictly stay because we are studying about the product rule. So let's get fluent with applying the product rule. So f of x equals x squared times right, so x cubed times 3x to the 4th plus constant 2. Okay, so once again realizing that we have a product here, and let's really apply the product rule, even though it might be a little longer than distributing the x cubed, but we purposely want to use the product rule. So f prime of x, here's how things are going to work out. This is u of x, that's how I recognize the product rule being used here. Multiplied all this in parentheses here is being regarded as v of x. So now f prime of x, the product rule says u prime. So u prime is x cubed, derivative, multiply with v. So multiply with 3x to the 4th plus 2, leaving it the same. Plus, and so now the next part, I'm going to keep u the same according to the product rule. So this is now x cubed multiply with, and so now derivative of 3x to the 4th plus 2. But see, this is only an indication of what to do of the problem, sort of like we are laying down a foundation for the next step. But this is not the final answer yet, but it's coming shortly. So now we are ready for our final answer. So now x cubed, taking the derivative of that, gives me 3x squared on that. And the product rule says we need to multiply with 3x to the 4th plus 2. This is v u prime times v. And now we're going to add. Now this time I am going to keep x cubed the same. But the derivative of this v function, term by term, we're looking at. Now the first term goes to 12x to the cube power, but now that second term here of my v function is a constant, so it goes to 0. So in other words, we don't need that anymore. Okay, and so technically we are done finding the derivative, simply just as a finding the derivative problem. Then we're done here. Now some instructor ask their students, some instructors, or it could be many instructors, ask their students to go ahead and simplify the final derivative right here. So that means from here we have to carry on with the algebra to multiply out, and combine like terms if we could. Okay, so in that way, so now when it comes to starting to do the product rule and the quotient rule, which we will shortly learn here, then make sure anytime you're doing a written problem, a written problem in finding the derivative, watch out for any kind of instruction saying, whether to simplify or not to simplify. So if your problem somewhere, anywhere in the beginning of your problem has a line say, do not simplify your answer, then this is right where you can leave it and call that the end of the problem. But if no special instruction, then usually we have to advance all the way to the very final simplified answer. And so here, since we don't have any specific comments about not to simplify, then I would go ahead and, so my f prime here, 3x squared times distributed into each term, I'm looking at 9x to the 6 plus 6x squared. And now for the next term right here, realizing we have a product here, then it's going to be 12 altogether, 12x to the 6th power. And I have like terms. So from this step and continue on and going further, it's only just the algebra work now. And so our final answer now, excuse me, but combining like terms here, we're looking at 21x to the 6 plus 6x squared. And this is where we can stop because we can no further simplify. Okay, so that is our example 1, part A. So now I am going to erase this. And let's now look at part B of the example. So part B here, we're asked to find about y equals, our function here is y equals x squared minus 4x plus 7. Allow me to write a little bit smaller than the earlier problem so that I can have more space. And in product with excuse me, x cubed plus 5. Okay, so once again, realizing we have a product right here, be ready for the product rule. And besides, the entire discussion here is about product rule, so we're trying to find as much opportunity to apply the product rule as we can. So in this particular problem, the way how I see our entire function that we're trying to find the derivative is a product of this, is where I can call that the function u, x, and this is v of x. Okay, and so now we are ready to apply, and the product rule now can be quite direct. We can immediately, we don't need to take any algebra step, we can just directly jump into taking the derivative. So u prime, according to the product rule, is now giving us the derivative of x squared minus 4x plus 7. So this is the derivative of u, or in other words, u prime is here, multiplied with x cubed plus 5. This is multiplied with v right there. Plus, now I am going to leave u the same way it was. So u x squared minus 4x plus 7. That's u from the product rule. And now we multiply with v prime. So this is how we're looking at v prime right here. X cubed plus 5. Take the derivative. All right. And so now at this point, and so far that's only an indication of what to do in the next step. But so now we are right about getting our final answer. So the derivative of u, or u prime is here. The actual derivative turns out to be 2x minus 4. And so up to this lecture, then I can start picking up pace in terms of getting any of these little power rules here to quick and short. Yeah. Okay. And multiply with x cubed plus 5. Okay, so that's u prime times v plus, and now I'm going to keep u the same because it's u times v prime. So x squared minus 4x plus 7, okay, multiply, and now this derivative, two terms are here, sum rule apply, and then that constant goes to 0, that goes to, that becomes 3x squared. So now we're, as far as only finding the derivative, we are done, because this is really our official derivative of this function. However, again, watch out that since the problem here did not have any special indication about do not simplify, then we have to, it is a responsibility for any students beyond algebra. Simplify your final answer. Okay, so now on my next board that I just spent some time erasing it, then we already found an answer. We already found the answer, but we would like to get to the simplified answer. So I am going to distribute out or FOIL out the products u prime and v. That's the first thing to do. And doing math is always from the left to the right. Okay, so in that way, now I'm looking at 2x to the fourth plus 10x, then and minus 4x cubed minus 20. Okay, that's after FOILing out the u prime times v. Then I am going to add, and now I'm going to quickly swing back at the other board. And so now I am going to distribute out that 3x squared for each term here. Okay. So what we're looking at now is going to be 6x to the fourth minus 12x cubed plus 21x squared. Okay, so now all terms are successfully FOILed out and distributed out. So let's now collect like terms. So there are 2x to the fourth, and x to the fourth is the highest power of the entire lengthy thing here. So now I am going to combine these like terms. So that gives me 8x to the fourth is here. And then after x to the fourth is x cubed right here. Let's collect all the like term x cubed. So now we're looking at minus 16x cubed. And now after the x cubed, let's look for x squared. And there's only one term with the x squared. So plus 21x squared, that's the square term. Okay, and now let's look for the x term, which is 10x is the only one. So plus 10x, and now minus 20, and that's the only constant term that we're looking at. Okay, and give me a moment to quickly double check right here. And yes, I believe that we have gotten the correct simplified final answer. So once again, my point is some instructor allowed their students to stop right here where it's immediately right after applying the product rule. But if that case would happen, then somewhere in the beginning of the problem there would have to be a line saying do not simplify or something like that. But then without any further indication, then any student is responsible to move on all the way to the end and simplify your answer into this form as being written on the board right here. Okay. And so now we are ready for the next discovery work. And so now after looking hopefully thoroughly enough at the product rule, and of course we will have plenty of opportunities to apply the product rule and the quotient rule. So for that reason, I don't need to bring out too many examples here. There will be a lot of opportunities later on where we can apply the product rule and the quotient rule. So let's head out to the next problem to promote the situation. So how about we're starting out with a given function. Given y equals And what I have here is x cubed minus 4x plus 2 over x squared. And let's find the derivative. Okay, let's find the derivative. So find dy dx. And so keep in mind, at this point, I still have not taught anything other than the 4 rules, the power rules with the other basic rules. And on top of that, maybe there's a 5th one, the product rule. But none of those is useful for something like this. Okay? And so, because what I see here is a quotient. And so, anyone viewing this video at this point, again, can start thinking, but maybe we can approach the problem as following, and then we don't need any fancy technique. Before finding the derivative, we can simply just recall from the earlier lecture that I have done that trick as well. We can break. So before getting the derivative, I can just simply rewrite my expression as so x cubed with x squared, because what's good for us, the advantage we have here is one single term in our denominator. So x cubed over x squared can be regarded as one fraction. Then minus 4x over x squared and plus 2 over x squared. Okay, so the rules of algebra allowed us to break a fraction into 3 separate little fractions like that. Okay, but now this is not our derivative work. This is just some algebra preparation step. And so we can simplify things a little further. So x cubed cancel with x squared, give me, okay, that first term becomes x minus, now this becomes a 4 over x, and this is 2 over x squared. Nothing can be changed there. And now we can trivially see that we can apply the power rule here by thinking of that as power 1. This here is minus 4x to the negative 1. So power rule can apply here. We only need the power rule for this. Plus 2x to the minus 2 power. So if we approach the problem this way, then dy dx will come out easily. If we would approach that way, then dy dx come out simply applying 3 product rule, power rule. 3 little power rules here to be applied. So on the first term, we're looking at 1. In the middle terms, we're looking at, there's a sign switch here, so be careful with that. X times, 4, positive 4 times x to the negative 2 power. And then there's a sign switch here again, minus 2 times x to the negative third. Okay, and that's how we're done for getting that derivative. But doing things this way, finding a derivative, the derivative in this problem is not getting us anywhere, in a sense that we don't need to learn a new technique. But then maybe we can blame that because the problem itself is too easy. Well, so things does not always stay easy until, or it seems like things stays easy until we have a different kind of problem. So let's say now we're given y equal x plus 1 over x cubed plus x minus 2. Okay, and so for something like this, then good luck with the breaking down. Okay, and so just like I said, things can remain easy until now when we start hitting something like this. Then we need a rule, a derivative method, a method to take derivative directly out from a quotient like this. And by the way, so in case you're not familiar with the term, but this is called a quotient. We have a fraction here, numerator and denominator. Okay, and so now to get into the idea right here, in this quotient, I can see this function on top right here, that x plus 1 can be referred as a u function. and all that in the denominator, and I'm intending to draw the brackets that kind of group all that. This function x plus 1, all of that is u of x. All of that x cubed plus x minus 2 is another function v of x in the denominator. So what we have here is u over v. Okay. So here's the idea of the rule I'm about to take. And without without mentioning its formal name at this point, then I am going the rule I'm about to show you. Here's how we're handling it. So dy dx, in this case, there's a rule that says we can find the derivative of u first, the one on top. So now I could have also mentioned, but earlier back in the product rule, it really didn't matter much about the order, which one to be started out first and which one is after. But now when we switch to this rule where it deals with a quotient like this, it is strictly important that we start out finding the derivative from the top one first, the top function first, then we moving our way down to the denominator. So u prime must be found first. We need to take the derivative of u. So now x plus 1, I'm going to take the derivative. And the rule I'm about to introduce now says, the rule that I'm on my way introducing, saying that we need to multiply the derivative of x plus 1 with x cubed plus x minus 2, keeping it the same. Okay. And instead of adding, so it's starting to look similar to the product rule. We take the derivative of one function. Here we have to start out, the priority one is the top one, so start out with the top one first. Take its derivative and multiply with the other one, supposedly the one at the denominator, but keeping it the same. So it's starting to look kind of like the product rule. But now for product rule it was plus. Here we are subtracting. So now I'm going to minus, I'm going to subtract. Okay. And what comes after the subtraction? So now I'm going to keep x plus 1. So it looks like this is, and no prime, it looks like this is u of x. And I'm going to multiply that with the derivative of x cubed plus x minus 2. So that's the rule I'm introducing right now. But then it's actually not done yet. So it looks like this so far looks like almost like the product rule, except we switch from the plus sign to the subtraction sign. But then things actually a little more than that. We need to produce as a fraction right here, draw that fraction bar. We are dividing by the square of x cubed plus x minus 2, the square of the denominator, or the square of v. And so this is actually the rule that I'm walking through right here is being referred to as the product rule. And so finishing our step, because so far it's only an indication of what to do. So now with that indication, take the prime of x plus 1. So now in my first step, x plus 1, take the prime, we're going to get just simply 1. 1 multiplied with x cubed plus x minus 2. Okay, and then subtract according to from the previous step. X plus 1, okay, multiply with, so now we're going to take the derivative of this x cubed plus x minus 2. So we're looking at 3x squared plus 1, and minus 2 becomes 0. But then don't forget, we need to divide by the square of our v function. So x cubed plus x minus 2 is being put in a square root, and I mean in a square, and all of that is in the denominator. And so I am going to end that little introduction problem right here. What's going on in this work we have done is what we so call the quotient rule. So on my next board here, so the quotient rule says anytime that you're looking at taking the derivative of a quotient. So in your quotient here, we having our function u on top being the numerator, our function v at the bottom here being the denominator. So if we are asked to find the overall derivative of a quotient like this, then what can we draw out as a conclusion right after that work we've done earlier? So it looks like we had to find u prime of x multiply with v according to what we have observed here. What we have observed here, u prime, this is u prime times v, and then minus, okay, that's a little something to remember. And the next part here is, it looks like I kept u the same and take the v prime. So for my next one right here, then we're subtracting. Now I'm looking at u of x multiply with v prime of x, okay, and then the quotient rule says we need to divide by the square of v of x. So this is what I refer to as the famous quotient rule. Every rule that we're learning is quite famous here because they are famous for their own usefulness. So quotient rule. So quotient rule. Okay. So now let's get started into an example, or let's continue our lecture here with a formal example. And so now into this example 2 right here. Let's find derivative, find f prime of x or dy dx, okay, our function in problem A. How about I am going to reuse, okay, so sorry for that, I forgot to switch the board, but so this is our example 2, okay, and we are finding f prime or dy dx. And as I just now said, let's reuse that introduction problem we've had earlier. So we were doing f of x equals x cubed minus 4x plus 2 over x squared. Okay, but this time we are going to purposely apply the quotient rule on top of this, even though we already found an answer by breaking this into 3 separate little fractions, partial fractions. That's the more formal term for that. But this time, let's directly apply the quotient rule on top of this. Okay, and so now I am going to see this numerator as my u of x right here, and this bottom right here, the denominator, is my v of x. Okay. And so what we have here is apparently u over q. I mean u over v. So applying our quotient rule, f prime is going to be, which is our main function, the derivative of our main function. Quotient rule says u prime. So u prime is the derivative of x cubed minus 4x plus 2. We need to take u prime, multiply with x squared, leaving it the same. And then quotient rule just now said minus, and then I'm going to leave x cubed minus 4x plus 2 the same in parentheses, no prime this time, and I am going to multiply with the derivative of x squared, okay, and divided by x squared all squared, the square of the denominator, according to what it's written in the quotient rule. So u prime times v minus u times v prime, okay, divided by v squared. All right. So now continuing into the next step here, then because so far this is only the introduction, I mean an indication of what to do next. But now the actual derivative is going to be, so derivative of this u function is going to be 3x squared minus 4. But now that's u prime. I need to multiply with x squared. Okay, and I am going to subtract. So now I'm going to keep u the same, unchanged, x cubed minus 4x plus 2, and multiply with now derivative of x squared is 2x, and in the denominator, since we have a square of x squared right here, so altogether it's x to the 4th power. So as far as getting the derivative done, we're done here. We're officially done. But as I said again, wait a minute. And the reason this time I use this same example, I use this example as being the same problem as our introduction problem, because so that we can, once again, I want to trigger up your comparisons. Our comparison about how come this final answer here look quite different and much longer, much more complicated. They're quite different from the earlier derivative that we have found. Okay, and so here's why. So right from where we ended our derivative, which many instructors or some instructors do not require their students to simplify, which is also some common practice out there in these days for many instructors. But in case that there's no special indication about simplifying your final answer, then you would need to go on further and simplify this. Okay, so in this problem right here, there are no special indication about do not simplify or anything like that. Then let's simplify this. So just want to be clear, we already found the derivative. What's happening next? We are going to find a way to simplify this down. Okay, so now back to my other empty board right here. So now I can distribute the x squared. I can distribute the x squared for each term here to obtain 3 x to the 4th minus 4x squared. Okay, and then I am going to subtract. Okay, and now I'm moving on to, and one more time, let's look back at the other board. But here I am going to distribute that 2x for each term here. Okay, and so now I'm looking at 2x to the 4th minus 8x squared plus 4x. And of course, that entire denominator from the earlier step, easy enough to remember. So x to the 4th. Okay, so this is our current derivative, but being developed a little further out, getting ready for the simplification work. Okay, and so now I'm looking at, let's now go ahead and remove this pair of parentheses. So 3x to the 4th minus 4x squared. And now taking out this pair of parentheses here requires some sign changes because there's a minus sign in front of that parentheses. So minus 2x to the 4th plus 8x squared, but minus 4x, and all over x to the 4th. And let's now combine like terms. Okay, and so far, well, and look on the bright side, it does look shorter and shorter. It does look more simplified and more simplified. So these two are going to be, combining these two like terms, we're looking at one single x to the 4th. Okay, and now it's the square term. Unfortunately, there are no cube terms, so we don't have to worry about that. Minus 4x squared, combined like term with 8x squared, so we're looking at plus 4x squared. Okay, and the minus 4x is by itself, no other like term with that, so minus 4x, and we're dividing all that by x to the 4th. So our expression does admittedly look more simplified. Okay, and so now in that way we're getting close. Not quite simplified though. I mean, we have some common factor here to recognize. Common factor among the x's here and can be cancelled with that x to the fourth, some x to the fourth in the denominator. And so, but to make the answer look really like the answer we have found earlier in the earlier solution, then we can break this down to x to the fourth over x to the fourth, doing the partial fraction thing, okay, plus 4x squared over x to the fourth, okay, and minus 4x over x to the fourth. All right, and so now this work here, okay, x to the fourth cancel with x to the fourth is a 1, okay, and now plus 4 over x squared and minus 4 over x cubed. So this answer does look like the answer we've had using the other technique before we apply the quotient rule. Okay. And so now let's try another problem here as part B of our current example. But for this next problem, I am going to stop at right when we had the derivative found directly from the quotient rule, and we don't need to simplify the expression. Okay, and so part B right here, let's look at our function y equals x plus 1 over x cubed plus x minus 2. Okay. All right, so it's a quotient, obviously. This is u of x, and this in the denominator is v of x. Notice in the way how our quotient look and in the way how we notate our function, this one here is u, this one here is v. Then we have to find the derivative of u first, whichever one in the numerator first. And by the way, for this particular problem, things can get a little challenge for simplifying. So how about for this particular problem, I'm only gonna show how to apply the quotient rule without the need for simplifying it. So your instructor might also have a line like this. Sometimes, do not simplify your final answer. Okay, so that means it's a good thing for us, less efforts for us here, because once we finish applying the quotient rule, then we can just leave it there as being our legal final answer for the derivative. Okay, so now again, quotient rule says, and with the quotient rule, then we can directly take the derivative. Okay, so with this quotient, the one on top is being the x plus 1 u, so we go u prime x plus 1 prime times v, meaning in product with x cubed plus x minus 2. Okay, and then minus or subtract. The quotient rule says minus, and now we're going to keep u the same. Allow me to erase a part of this. Okay, so now minus, I'm going to keep u the same. X plus 1 is there, multiply with v prime. So v prime here is the derivative of x cubed plus x minus 2. Okay, and we're dividing all that by the square of the b. So x cubed plus x minus 2 being all squared. Okay, and so now our victory is right around the corner. All right, so dy dx in this case, getting things done, I am going to, let's look at So the derivative of x plus 1 is simply just 1, but multiply with x cubed plus x minus 2. Okay, and minus, and now I'm going to keep x plus 1 the same. This is u now, but multiply with v prime. And v prime is x cubed plus x minus 2. I mean, miscalculated. 3x squared plus 1. All right. And we're dividing that by x cubed plus x minus 2 all squared. Okay. And so, of course, with that add-on instructions, do not simplify, intended for not simplifying the final answer. Then this is where we have successfully found our derivative of that function by using the quotient rule. Okay. All right, and so now with all that rules we have learned, and I just now realized that we haven't done the tangent line problems for about 2 lectures now. So let's, before we complete out with this, before we completely move out from this lecture here, let's do another tangent line problem. So the idea now is that derivative techniques are to be aimed at getting your derivatives successfully, but finding any derivative is for getting the slope of the tangent line. And so after learning a lot more derivative rules now, let's get ourselves into another example again about finding a tangent line, equation of tangent line problem. So I'm going to say find the equation of the tangent line to the function of y equals x minus 1 over x plus 2. Okay, at x equals 1. Okay, so this time we have a function and we have a given point again. Okay, so I will, as I said in some of the earlier lecture, that I will keep occasionally deliver an example where it asks anyone to find the equation of a tangent line, because that skill of being able to find the equation of a tangent line is so important. What matters for us now is that different tangent line problem, we are being exposed to different kinds of functions. So in this function here, what I have now is a quotient, x minus 1 over x plus 2. But the main structure of finding the equation of a tangent line remains exactly the same. So remind again that any line equation must be in the form of a y equals mx plus b. But our equation here, our line here is a special line. It's called a tangent line. So I am going to use a subscript, capital T, to indicate this slope right here is the slope of the tangent line. Okay, so as long as we can find out what the slope of our tangent line is and the y-intercept value of our tangent line is, we're done completing that equation. And so now the first big step here is to get the first big step. And like I said, again, being the instructor here, I'm going to have to really break it down as a planning of what steps we need to go through or what stages we need to go through. So the first big step is to obtain the slope of the tangent line. But before we can actually get the slope, then a real big step within this part right here is to find the dy dx, the derivative. So right here to find our derivative, because remind yourself again, the whole point of finding any derivative is to eventually, for substituting in that given value, to get our slope of the tangent line at that point. Okay, and also remind yourself that without any given tangent value right here, tangent point value, then the derivative is simply just the general expression to quickly calculate the tangent line with slope anywhere on that curve. And so dy dx here is going to be, according to the quotient rule, we're looking at x minus 1 prime times x plus 2 minus x minus 1 times x plus 2 prime. And we're dividing that by all that by x plus 2 all square. And here is just a setting up indicating that I'm about to use the quotient rule to get the derivative of my function y equals x minus 1 all over x plus 2. And so continuing further, I'm now looking at dy dx truly as so derivative of x minus 1 is just 1. So 1 times x plus 2 is just simply now x plus 2 minus now x plus 1, but the derivative of x plus 2 here is just 1 again. So I'm looking at only minus x plus 1. And we're dividing all this here by x plus 2 square. Okay, and so my final, well, for a problem like this, it's simplified. It's simple enough that we can do some mild simplification. So x plus 2 minus x plus 1 in parentheses, that means we can do x plus 2 minus x plus 1. So all in the end, well, or maybe I should write it down, x plus 2 minus x plus 1 all over x plus 2 in quantity square. Okay, and so on my next board, then dy dx equals, and notice how we have opposite terms here. There's x and minus x, and these two terms can be combined as like terms. And so now I'm ready for my final derivative here. So we're looking at 3 over x plus 2 all square. Okay, and so now we've got a general derivative, which means anywhere on the graph of this function. Okay, anywhere on the graph of this function. And we don't even have to graph the function. We just know that, hey, if this function gives us some kind of graph, then anywhere at any x values on this graph right here, we can obtain the slope of the tangent line by using this little derivative formula. Okay, and so that means really we get to what we need now. The actual slope of our tangent line now is equal to our dy dx that we have found, but this time particularly substituting in x equals 1. Recall for yourself about this this symbol I introduced in the earlier lecture. It's just simply indicating that from where our previously found derivative, then we are now going to substitute or evaluate in the input x equals 1. So that means our slope of the tangent line really equals to 3 over 1 plus 2 in parentheses square. So that is the same as 3 over 9, which is a 1/3. All right, so we now found the slope. And so we already got a little bit half of our work done. So our equation up to this point is going to be 1/3 x plus b. We are missing out that y-intercept value right there. And so the next step now is to nail down our tangent point. Okay, so for our tangent point here, when x equals 1 as given, then the y value of the tangent point is going to be, we're substituting that x value into our beginning function. And I have to emphasize that again, we substitute our x value into the beginning function. So in this case, we are looking at 1 minus 1 over 1 plus 2, and the answer overall is a 0. So our tangent point is actually 1, 0. Okay, and so now we got the tangent point ready. So the rest of the work is now clear. Okay, And so with our halfway done equation at this point right here, we can go ahead and substitute our tangent point x for x, y for y into our currently halfway found equation of the tangent line. And so now we're looking at 0 for y equals 1/3 times 1 plus b. Okay, and so in that case right here, quickly we can find out that our y-intercept b value is negative 1/3. And so, and of course, viewers of this video are at calculus level, so I'm not going to bother too much about showing the clear steps of how I got b equals negative 1/3. I mean, it should be a very simple algebra problem. And so now, getting b value, and I shouldn't put that in a box too rushly because that's not our answer. Our answer is the equation. And so now at this point, we are ready for completing our equation. So we got slope being 1/3, and we just now found that our y-intercept value is being a negative 1/3. So final equation of the tangent line is y equals 1/3 x minus 1/3. And that is how we found another equation of the tangent line. And this tangent line here is tangent to our whatever the graph of x minus 1 over x plus 2 at the point x equals 1. Okay, so here's our function, x minus 1 all over x plus 2, and at that specific given point x equals 1. Okay, and bear with me for another minute or so because I would like to show the graph of that. So let me put that on screen first. So let's have a quick look at the graph. And so my aim is that almost every example that involves a tangent line, then I am going to quickly demonstrate the tangent line. Okay, so let me quickly prepare that. All right, so here's our graph right here of our. So the red curve right here is our function, that x minus 1 all over x plus 2. Okay, and so the tangent point is right here. With x equals 1, we have the point 1, 0. Okay, 1, 0. That's our tangent point. And so now I am going to put on the tangent line. And so that's how we found the equation of tangent line. This line in green right here is that line with, you can see that our slope is 1/3. And so 1/3 is 1 rise. Think about from where the tangent point is, right at that point with the grid right here, 1, 0. So only rise 1 square in the next one, but over by 3 squares. So that's why it got slope 1/3. And if we're looking further into this y-intercept right here of our green line of the tangent line, it's intercepting with the x-axis, I mean the y-axis, right at y equals negative 1/3. So completing it all together, this line in green here has that equation 1/3 x minus 1/3. And that is the tangent line for our actual graph in red right here, but at that point, that particular point, x equals 1.